Yeah. So I think we are live. Uh,
Okay.
yeah, I'll just give a quick introduction, sir, about you. If Sasanko, if you can confirm that we are live. Mm.
Yeah, it is showing like live, okay, in the content section.
Okay, so then I will start.
Yeah, sure.
Okay, okay. So, very good afternoon to one and all present virtually today at this, the 11th version of the I Technical Lecture Series. Today, we are grateful to have with us Nabarun Goswami, sir, who is currently pursuing his PhD from Tokyo University, Japan. In this talk, Sir will mainly cover his journey from being an engineer to a researcher and at Sony. And then he will also make a transition back to academia first, as he made a transition back to academia first as a master's student, and then he went on to become a doctoral student now at the University of Tokyo. He has also completed his bachelor's degree in electronics and communication engineering from Tezpur University, where he developed an interest in multimedia technologies. His primary research interest is in the confluence of audio, language, and artificial intelligence. The talk will be centered around audio source separation, and he will introduce his current research areas, which is speech synthesis. We will also be talking about source separation in terms of music, as well as separating individual speech segments from mixed speech with multiple speakers. As for speech synthesis, Sir will be giving us a brief overview of the task and some of the current methods for synthesizing natural speech. So, without any further ado, I would like to hand over the session to Nabarun sir. And for those who are watching on YouTube, if you have any questions, please drop them in the chat box, and we will ask them here. Okay, over to you, sir.
Thank you, Abhigyan. Let me just share my screen. Yeah, can you see my screen now?
Yes, we can, sir. Yeah, we can see your screen, sir. Sir, we can't hear your audio, I think.
Am I audible now? Hello?
Yes, sir, you're audible. Yes.
Okay, okay. What about now? Am I audible now?
Yes, you're audible, sir.
Okay, great. Hello?
Yes, sir, we can hear you now.
Am I audible? Am I audible? Hello?
Yeah, we can hear you, sir.
This is.
Hi Nabarun, can you hear me?
No. Okay. Hello. Hmm? Sorry, I'm not sure what's happening. As soon as I share my screen, then the audio kind of cuts off. Can you hear me now or not?
Yes, sir. We were able to hear you actually then.
Wow, it's. Okay, so let me try again. Hello, hello, hello. Hello.
Yes, sir. We can hear you.
Okay, I'm still. Okay, should be good now. You can hear me, right?
We can hear you, sir. Now.
All right. I don't know what is the problem. Okay. So, sorry for the delay and like the technical difficulties. So my name is Nabarun Goswami, and I will be talking about what it takes to go from an engineer to being a researcher. And this is as part of the Assam AI Initiative Technical Lecture Series, and I'm really grateful to the organizers for having me here. Okay, so first off, like a kind of small introduction about myself. As for my education, I did my bachelor's in electronics and communication engineering from Tezpur University. After that, in 2012, so then I did my master's in mechanoinformatics from the University of Tokyo in 2021. And just from like this month, I've started as a PhD student at the Advanced Interdisciplinary Studies Department at the University of Tokyo. As for my work experience, I'm currently working as a junior research engineer at Nablas Incorporated, which is a startup, and I'm currently conducting research on deepfake generation and detection. So, okay. Prior to this, I was also working like as a programming tutor for an organization called Tokyo Coding Club. And before that, I worked for almost 7 years as a technical specialist at Sony. My interests are like apart from my work, so I am like an amateur cook. So really like cooking. I like traveling, photography, and also like aquascaping, so keeping fish and aquariums and stuff like that. Okay, so coming to the question, right? So engineers versus scientists. So the scientists kind of seek the perfect understanding, but does not bother with execution. So the scientist doesn't really care about whether it works or not. He just needs to understand. Whereas the engineer kind of seeks like perfect execution, but does not bother with understanding. So like Einstein had once said, like scientists investigate that which already is, but engineers create that what there has never been. So scientists think of stuff and the engineers can create the stuff, right? So with this kind of starting off, I'd like to start off with my the first phase of my journey, which was like engineering as a software engineer and later the technical specialist at Sony. So where I worked on various multimedia technologies, we developed proof of concepts, and we wrote some patents. So I'll just introduce some of the projects that we did. So first one was a device and method for generating a panoramic image. Now, this is an interesting one because this is not from a regular camera. So this is from a field called light field photography, which are special cameras which capture light from a lot of, like, all directions, the light that is coming in, instead of the traditional camera, which only focuses on the light which is coming in straight at the lens. So in the light field photography, it basically allows us to kind of do dynamic refocusing. So you can adjust the field of view dynamically after you have captured the image. For normal cameras, you need to do kind of image manipulations, and you have to apply some kind of algorithms to do that. But in light field photography, it's pretty straightforward. So using this light field photography or images, so we basically try to make like a prediction of the important subjects in the image, right? So we try to predict the different subjects in that image, like the painting or the person or a different person, right? And based on that detection, we kind of do like an efficient and smart stitching of the successive frames. So as you are taking a light field photograph, like in a panoramic mode, so we select salient subjects in those frames, and then adjust the field of view to those subjects, and then stitch them in a seamless way to generate a panorama where the field of focus is constantly changing onto the predicted subject or the desired subject. So this was a patent which was published in the US patents. Okay, so next one is called system and method for sharing multimedia content with synchronized playback controls. So this, I'm not sure if you have heard, but there is Apple's new Share Play feature, which is coming to like the FaceTime calls, where when you are FaceTiming, you can basically watch a movie together or listen to a song together, and each of the participants can kind of control the playback and synchronously. So each of you will be at the same page. So this new feature is really very similar to this patent, which we developed back in 2016. So basically, it involves sharing of multimedia content between like various connected devices with shared playback controls. So if I'm sharing to you and we are listening together, you also have the ability to rewind, fast forward, or those kind of playback controls. And another interesting part of this was that it was done with like a low latency network stack using distributed IoT edge-based networking. So which basically meant that the latency was really low for like sharing of the playback controls. Thirdly, there's this work which is called system method for processing video content based on emotional state detection. So this is basically when you're watching some sports or something like that. So we try to recognize the emotional state of the viewer based on like the facial expressions and body language. And apart from that, we also recognize some interesting things which are happening in the game itself based on sensors and the video data. So this project was kind of combines the user space and the broadcast space, right? So there's some things which is happening in the broadcast space, and there is emotion recognition happening in the user space as well. And then based on the correlation of these two spaces, we kind of generate highlight reels, or you can have like different, like if the user is getting bored, you can switch to another kind of content, or things like that can be achieved. The fourth one is for kind of generating multi-dimensional videos. So if you have seen the Olympics coverage this year, so you might have seen those views when, like, let's say for a long jump, the view kind of rotates and gives you different perspectives. So there is an array of cameras which are placed around the specific place of interest where the action is going to happen. So in this work, what we did was we tried to predict like the impact of a player. Like for example, if there are 11 players in a team, this algorithm tries to predict which is the player at any moment who will have the most impact in the game. And then what we do is we predict like upcoming activity of interest. Like for example, if let's say Messi has the ball and like it's kind of obvious that he's going for goal, right? Or he's at least the action is going to move towards the other team's half. So in this way, they're based on various factors of like we have like sensors and like the multi-view camera arrays. Based on that, kind of predict the upcoming activity of interest or the location on field where the action is going to happen. And then we kind of redirect part of the 3D broadcasting setup to capture the predicted activity of interest. So this is basically you have your cameras on the current state of play, and then some cameras kind of switch into the state of play where the next predicted impact or activity of interest is going to happen. So that the broadcast is kind of one step ahead of the actual gameplay. Sometimes it might not work, obviously, but then if it works, you are there to capture the moment even before when it happens, right? Rather than changing the game, you are ahead of the game. Okay, so these were the kind of proof of concepts and patents that we developed as part of my like engineer role in Sony. Then I kind of made a switch into AI, like because I was doing a lot of predictive engineering, right, using existing methods to try and build some solutions for products and stuff like that. So then my interest started getting into the research side of it. So I got into a research team in the audio domain, and we worked on audio source separation, mainly music and speech. So now what is audio source separation, right? So in this image, so this basically tells us about the music source separation. So you have these songs, like various kinds of songs, which are recorded, and you have like, if it's a stereo, you have like a 2-channel song or a single channel song, or if you have like a home theater, you can have like 5-channel songs. But usually the number of channels is less than the number of instruments. You have, let's say here you have like four instruments. You have the guitars, the drums, or the bass, the drums, the accompaniments, and the vocals, right? Which are all kind of mixed, and you cannot really separate them like directly, right? So for this, we use the source separation algorithms, which are like data driven and like trained using deep learning technologies to separate the input mixer sound into its constituent sounds. So this is what source separation is. Now, instead of music, it can also be like mixed speech. If multiple people are talking at the same time and there's overlap, you can try and extract the different speaker speeches in the same fashion. Now, a brief introduction about the time frequency audio representations. So you might have seen this before, but I just thought to give a brief overview. So basically, we use something called as spectrograms, so which look like this. So you have a time axis and a frequency axis. So how we get this is basically the signal is kind of windowed, and then like a Fourier transform is taken for each of the windows, and they're stacked together to get the spectrogram. And these colors kind of like signify the energy of a particular time and frequency bin. It's called a time and frequency bin. So we have this, the upper picture is like a linear spectrogram where the frequencies are linearly arranged. But in when we hear, our human hearing is more in the logarithmic scale, or kind of like it's called a Mel frequency scale, right? So you kind of take the log and then do some kind of filtering to arrive at a kind of a spectrogram, which is in the log scale where the frequencies are in the log scale. The time axis remains the same. So this is the magnitude. So most of the methods that are used for source separation use the magnitude spectrogram. But there is another part to the Fourier transform or the spectrogram, which is the phase, which is usually neglected, or the mixture phase is directly used for the outputs as well. But we'll see that we also propose some methods for modeling the phase as well. Okay, so first of all, I'd like to introduce this work, which was done by my team. So this was published before I joined the team, but this is kind of important for background for the next series of works that I'll be explaining. So this is called multi-scale multi-band densenets for audio source separation. It was published in WASPA in 2017. So what it does is, so this blue thing is basically your spectrogram. So you have the time axis and the frequency axis. And what they did was they kind of split the frequency axis into several bands, and then applied like a densenet, like a M densenet, which is shown on the right side, where you have like dense blocks followed by downsampling layers, and then you have upsampling layers, and then more dense blocks and some skip connections as well. So these M densenets, or this is called multi-scale because there's downsampling and then upsampling, so you're analyzing the signal at multiple scales. So these M densenets are used for several bands in the input time frequency spectrum. And then you also have one like a full band densenet. And finally, all these are combined into a single dense block to get the output. So the advantage of this is that for certain instruments, like for example, the bass is concentrated more in the low frequency regions, right? But if you are looking at some kind of like in drums, like cymbals and stuff like that, those are really high up in the frequency spectrum. So having separate like networks for each time frequency band or frequency band is useful, because then you can like employ resources as per the task at hand. Like for the bass, you can have a bigger M densenet for the low frequency band than the one that you would use for the high frequency band, because there is virtually no information about bass in the high frequencies. So this got like pretty good results in terms of SDR. So SDR is basically signal to distortion ratio. It's a measure of how well you have separated a source from the mixture. So as you can see, the MM densenet and MM densenet plus. So plus is basically just the same network, but trained with more data, performs quite well. And also another thing to note here is very important is that the training time and the number of parameters is far, far, far less than any of the previous methods. Like here, the previous methods have like 8 million or 6 million parameters, whereas the M densenet and the MM densenet have only in terms of like thousands, like 300,000 and 160,000 parameters. And this is like the box plot of the same results here. Now coming to the next work, so this is called MM dense LSTM. So this is related and quite similar to the previous one, but instead of having just the M densenet as in the previous one, we also use like LSTM layers in the middle. So why do we do that is kind of to first model the spatial features in the spectrogram with the densenets, which are convolutional. Followed by, we do the LSTM, which is kind of a recurrent architecture. And then it allows us to find kind of temporal correlations among the data. And that kind of helps to improve the performance further. And we tried various different like placements of the LSTM layer. So the blue one here is the LSTM layer. So we put it like after the dense blocks, or we put it before each dense block, where we put it in parallel. So we found that like as I told you, based on intuition, the after is kind of the best performing, because the convolutional part extracts the spatial information, and then the LSTM can process the spatial information in the temporal direction as well. So So this method we submitted this method to the MUS 2018 challenge, which is like a unmixing professionally produced music. So it was held in 2018, and we actually got the best scores for this. There is a website which I'll show you some samples once the presentation is over. So and you can see that the MM-Dense LSTM performs much better than any of the previous methods here. Okay, so next is called PhaseNet. So which is basically, the title is like discretized phase modeling with deep neural networks for audio source separation. So this work was done with Purvi, I think, who was also part of the technical lecture series of a little while ago. And so it was done in 2018. So basically, if you see here, so the right side picture depicts the phase. Now, the source magnitude and the mixture magnitude, right? So what does that mean is that this is the clean source. This is one source, let's say the guitars or just the drums. And this is the mixture, which means that it's a combined of all the different sources, right? But when you look at the phase, it looks completely random. You cannot really tell these two apart. In the magnitude, you can kind of tell it apart, like which is source and which is mixture. But in the phase domain, you cannot do that. Now, there have been approaches which have tried to model phase using regression-based approaches, but kind of there is a problem in regression-based approach because there is a discontinuity. As you know, the phase is kind of circular, right? It is periodic. So you start from 0 degrees and then you go back and come back up to 360 degrees. And then it's kind of, again, it starts from 0, right? So there is a discontinuity point. So what people do is they kind of unwrap the phase. So if it goes beyond 360, they'll go to 370, 380, 390. But then what happens is for a very long audio sequence, it becomes really unbounded and it becomes really difficult to model. So what we did was we thought of quantizing the phase. So instead of having it as a continuous variable, we proposed to kind of frame the problem as a classification problem by quantizing the phase. And we did some kind of tests or like listening tests. So, and we found that if we quantize the phase like into, let's say four levels, right? So what does 4 quantization level means? So that means that any phase which is between 0 and 90 degrees will be same. Like we just quantize it to one value. Anything between 90 and 180 will be quantized to one value. So basically, we just take the quadrants as the representative of the phase. So when we take 4, it's kind of like all the listeners were able to tell which is which is the quantized phase, which signal has the quantized phase, and which signal has the non-quantized phase. But when we go when we quantize it at level 8, which is basically kind of 2 values for each quadrant, so we found that 50% of them could not really tell which was the real and which was the quantized. So it kind of it's a random chance, right? 50% is a random chance. So we realized that we can actually quantize the phase and then model it in the quantized domain as a classification model. So this was like the method. So where we have the phase, and then we also add like the log magnitude ratio. So now why we do that? So why do we do that? So about phase, so the phase of the mixture, like when you mix multiple signals into one signal, the phase of the final mixture is dominated, or it's dominantly affected by one of the sources if the magnitude of that source is dominant in the time frequency bin. That means if in a time frequency bin, if I mix 4 sources, one of them is, let's say, has energy of 90, others has 3 and 4, then the phase will also be dominated by the phase of that particular source which has the highest energy. So, so similarly, if the magnitude has a similar level or lower level than the interference, the phase could be kind of tweaked. Right? So basically, what it means is that the mixture phase is probably the most closest to the target phase, right? But then it's not always the case. It's not the case when the energies are quite similar. So in that case, we kind of use, or we take that into advantage to kind of model the phase in this work. So for this, we feed that log magnitude ratio, which allows us to kind of have a correspondence between the phase and the mixture spectrogram magnitude. So coming to the results of this, basically we kind of had two baselines, the lower baseline and the upper baseline. So the lower baseline is basically when you use the mixture phase, right, which is like the corrupted phase. Upper baseline is when you use the actual phase of the ground truth signal. And then DNN-R is basically a DNN model which is trained in the regression way. And PhaseNet is trained with the proposed method. So the best case is like the upper baseline, which would be like the ideal value, right, or the ideal level of performance. But the PhaseNet does not reach that ideal level, but then it performs much better than like the regular regression-based methods. And so we did this for like speech enhancement, where we try to enhance the speech from noisy backgrounds, as well as for music source separation. Now this plot kind of shows the accuracy, so which means that it's a histogram of the index difference between the quantized targets and its estimates. So that means like 20% of all the estimates were correctly kind of quantized, whereas the mixture would be only at 15%. So for like the index difference of 0, which means that this is like the perfect quantized bin that has been predicted. So as you go if you increase the index difference, that means the predicted index and the actual index is like really different. We see like only very few percent of the estimates go into that category. Okay, so next is recursive speech separation for unknown number of speakers. This was published in InterSpeech 2019. 2019. Okay, so this is a very kind of simple approach, but one which allows us to kind of separate speech beyond 3-speaker mixture. So this was one of the first methods to show that it is possible to do speech separation for more than 3 speakers, even when you don't have training data for such more than 3-speaker mixture. So for this, what we do is it's kind of like an iterative method. So where from the mixture, we first do a one and rest separation. That means we separate one speaker, and then the other is kind of like the remaining speakers. And then we take second iteration to kind of separate again one speaker and the remaining. But since it's a 3 speakers, so the remaining is kind of like one speaker as well. So we can just stop doing that here. So we use kind of like a binary classifier to detect whether a signal has one speaker or it has multiple speakers. So to achieve this, we kind of modify the permutation invariant training, where we have like clean speech and clean speech, which are like the estimates, and which goes into this kind of pairwise score. So each of the estimates are kind of compared with both the targets, because we don't know which so there's no way to tell which one is like single and which one is 2 speakers, or which one is speaker 1 and speaker 2. So we can separate them, but there is no easy way of knowing which is which. So how they optimize it is basically they take the pairwise score for all the permutations between the estimated and the clean speeches, and then find the errors and then take the minimum error. So they train it with the minimum error when you do this. So we modified this PIT into like, and we call it like one and rest PIT. So it's basically the same thing, but instead of having like the second part as the clean speech 2, we have the second part as like the sum of the other speakers' mixed speeches. So if you look at these results, we get like really competitive results, and like especially for like 4 speaker mixtures, so which is not reported by any other work till this paper was published. And we also kind of checked the viability of separating more than 4. Like we tried up to like 50 or 60 speakers, and we saw that we could actually do speech separation to a relatively good level, even for like 50 speakers. So up to 10 speakers, we can do really well and separate out the speech like quite well. But after that as well, we can still, I mean, it's difficult, but then we can still do to some extent. Okay, so next, I've discussed about my work at Sony. So next is a transition phase, which is the application and admission to Tokyo University and how I got here. So I basically came through a scholarship called the Japanese government MEXT scholarship. So you can find the details about it here. So there are a variety of different categories where you can go as a student, and they will fund your studies. So the students who are like non-regular students, they approximately receive like stipends, which are like roughly between 143,000 yen to 145,000 yen, which is like almost like 1 lakh rupees per month. And the good thing about this is that the tuition fees are exempted, and also they provide a round-trip airfare for the duration. Like you can go once and you can come back. So the flow of the application and admission process was something like this. So there was an interview and selection by the Japanese embassy in India, after which I had to contact the professors and acquire an acceptance letter. So they have to agree to accept me. And then the final document check and confirmation of the scholarship is done by the Japanese government once I complete the first 2 phases. Then you arrive in Japan as a research student. Now, this is a little different because you don't directly arrive as a master's student or a PhD student. So all international students come here first as a research student. And they take, like, some might not take, some might immediately write the entrance examination, but most of the students, they usually take 1 semester to kind of prepare for the entrance examination, which is held twice a year. And the entrance examination is kind of at the level of gate based on your departments. And it's a subjective test, so you have to actually write the answers. So it's not a multiple choice. So once you pass the entrance exam, you can start your degree course, like whether it be master's or a PhD. So this whole process up until the passing of the entrance examination takes about 1 year. So it's not a very fast process. It takes its own time, but it's a pretty good way to get into Japan if you want to look for higher studies here. Okay, now I'll briefly discuss about my current research, which I'm doing at the University of Tokyo since 2019. So I'm basically working on speech synthesis. So I'll give some backgrounds, motivations, related works, and such like that. So the overview is that like the ability to synthesize natural speech from text is important for intelligent systems, right? Because it enables like human-like communication with machines, improves accessibility for people with disabilities, etc. And you can see this in like robots, personal assistants, voice synthesizers, etc., etc. So basically, the system looks like this. So there's an example sentence. So there's a text, which can come from a variety of different sources, like dialogue systems. It can be user input or ebooks, etc. It goes to a text-to-speech or TTS system, and which produces the speech. Now, the advent of machine learning has enabled like really high-quality TTS systems to be built. Coming to single speakers TTS, so it's usually a 2-step process where first, from the text, a spectrogram synthesizer synthesizes a MEL spectrogram. So some examples of very successful spectrogram synthesizers are like Tachotron 2 and Transformer TTS. This spectrogram is then consumed by a waveform synthesizer, which synthesizes the speech waveform conditioned on the spectrogram. So some really popular ones of waveform synthesizer are like WaveNet, WaveGlow, Neural Source Filter, etc. Now, in this pipeline, there is also a scope to control the speaking style, like the rate, pitch, stress, emotion, etc. So where a different utterance of the same speaker might be used to do a style conditioning for the spectrogram synthesizer, right? So when the spectrogram synthesizer is synthesizing the MEL spectrogram, it takes into account the style of the speaker through the style conditioning module. So one example of this is the global style tokens proposed in 2019. Now coming to the multi-speaker TTS, so which is the basic or the backbone pipeline is the same as single speaker TTS, but now an additional speaker conditioning is done, which can be in the form of a speaker ID, which is like a direct conditioning, right? So you know which speakers. But it only works for speakers in the data set, and the speaking style is sometimes not captured. Like if the same speaker speaks in different styles, that is difficult to be captured. The other way is to take a target speakers like a reference utterance or a reference speech sample and do some kind of a speaker encoding and then use that encoding to condition the spectrum synthesizer. So in this, the zero-shot speaker adaptation is possible, which means that even for unseen speakers which have not been seen during the training, you can actually synthesize speech in a manner which kind of tries to reflect the qualities of that person's reference speech. However, the speaking style is still not captured sometimes. Right? Some examples of this is like the speaker verification TTS and multi-speaker Decotron, which have been quite successful. Even in this one, you can control the speaking styles using a different reference utterance to do style conditioning. So it's kind of like a two-step. So first you condition on the speaker, and then you separately condition on the style. An example of this is Mellotron, which uses the speaker ID along with the global style tokens, as we saw in the previous slide, and like explicit pitch contours and stuff like that. Another aspect of TTS is like the availability or unavailability of data. So in a recent study, it was found that more than 88% of all languages have very little data, like whether labeled or unlabeled. Right? And like more than 8% of all languages have a lot of unlabeled data, which is this part of the graph, but very little labeled data. And over 2 billion people speak these languages in this world, right? And I think this is true for a lot of Indian languages as well. The question is, can we improve the inclusion of these low resource languages in the recent advances in NLP and speech technologies? So these are some of the questions that I'm trying to tackle in my PhD research. And secondly, there is the tonality in languages, right? So this is basically the pronunciation and speaking tone, they convey different meaning for the same text. So this example, I know you'll not be able to read this, but this basically says like, I don't drink beer. But when you say it in a flat tone, it's a statement that I don't drink beer. But when you say it in a rising tone, then it becomes a question like, won't you have a beer? So there's difference for the same text based on the contour of how you are like putting stress or how you are raising or falling your tone, it conveys different meanings. And more than 1.5 billion people like speak tonal languages, and most of these languages are low resource, right? So many African, Asian, European languages are tonal to varying degrees. So in current systems, right, the important factors for understanding the meaning of like a word or a sentence is usually like the text itself. So people they put like explicit accent marks or question marks, grammatical marks to emphasize or differentiate which is kind of which meaning is being conveyed, or the context, right? So instead of looking at this sentence in isolation, you look at it in a paragraph and then see how this sentence interacts with its nearby sentences or nearby words, so that from the context you can infer the meaning. So the question is, can we like kind of improve language modeling by making the models aware of phonetics, right? So this pronunciation and speaking tone comes from the phonetics. And then can we make our models like the NLP models, which are primarily text-based, can we make them aware of phonetics and improve their performance? Right? So these are some of the questions that I'm kind of trying to address in my PhD. So the objective of my research in PhD is kind of to bridge the gap between the linguistic and acoustic modeling, which is kind of like you kind of have like separate linguistic models which are trained on text data, acoustic models which are trained on like speech data, which are not like labeled or not transcribed? And can we have some kind of a common representation for this? Which common representation can then be utilized for applications such as text-to-speech, question answering, speech recognition, and lots of other tasks which involve language and speech. Right? So these can be semi-supervised or unsupervised. Okay, so I think that is almost the end of, not almost, it is the end of my presentation. So the last thing I'd like to say is keep imagining, because whether you are an engineer or a scientist, like imagination is what drives either of them, right? So if you don't have imagination, you'll not be able to build something new or find new things in existing, like find new insights in existing systems. Right? So my last message is that keep imagining. Yeah, thank you very much for listening. And if you have any questions, I'll be happy to take them. Thank you.
Thank you so much, sir. I think it was a wonderful and engaging talk. Yeah, we are checking on the questions.
Okay.
Yeah. In the meantime, I have a question. Nabarun. Am I audible?
You are audible, but the voice is like really low.
Okay. So am I audible now?
Yeah. Let me. Yeah.
Cool. Yeah. So in one of the slides, you have referred to multi-speaker TTS. So I was just wondering if there has been any research on code switch speech, like the speech where the speaker alternates between two or more languages.
There have been some work on that. So I have not covered it in the presentation, but then there are recent works where they do code switching, and also like. But it's not like end-to-end methods are relatively sparse in that field. So they usually have they would use speech to text and then do the code switching and then do the text to speech again. So they kind of do like a split pipeline kind of method where they use existing or existing well-trained methods for each of the domains and then kind of build some pipelines. But there have been some recent works which have tried to do code switching as well in an end-to-end fashion. Yeah.
Great. And how has been the experience of coming back to academia from industry after so many years? And to add to that, so do you have PhD coursework in Japan? So do the PhD students have to do any coursework when they join any institute?
Yes. So. Okay, I'll take the first question first. So you asked how has been the experience of switching from the corporate to academia. So I think being in both now, I kind of appreciate there are pros and cons in both. So when you are in one, the other one seems like the grass is always greener on the other side, right? But it has pros and cons, and it's both. Like in the corporate sector, you are sometimes you are kind of restricted by the things that you can do. You have to stay within a particular a bounding box of your project or of your a specified research. But you have kind of like a structure in place where you are expected to give deliveries and stuff like that. So you know where you stand in the project as you go through it. But in academia, what happens is you have the freedom to work on anything under the sun. So there are sometimes tendencies to kind of go on a certain tangent path, and then you have to kind of recorrect yourself to bring you back to the main path. So yeah, that sometimes happens. Like if I'm working on something, I think I find something really interesting and I kind of go down that rabbit hole and I spend some time on that, and then sometimes it's fruitful, but sometimes it's not. So I have to kind of come back to the original one. So there are pros and cons to both, I'd say. And secondly, yes, the PhD courses do have coursework, but it's very less. It's I think it's about 2 or 3 courses that we need to take over a period of 3 years. So in Japan, PhD usually is done in 3 years. So there are cases where people get it in 1 year or get it in 7 years. But then The average usually is 3 years in Japan. So I think in India it's more like 5 years, but in Japan it's 3 years. So they expect you to do the same amount of work in 3 years, research-wise. So the coursework load is slightly less than like maybe some other places. The same is the case in master's degree as well, actually. So the coursework is not very taxing. So they put more emphasis on the research and your thesis and the thesis defense rather than how you performed in your coursework and how many credits did you get. Like you can just get the minimum number of credits required. So you don't really have to, if you have more than the required number of credits, it doesn't really add anything to your experience apart from, of course, you can take if you want to learn more, but yeah, they put more emphasis on the research here. Yeah.
So we have a few questions on YouTube. First one is, yeah.
Sorry, your voice is kind of...
Hello.
Yeah.
Is it better now, sir? Am I audible?
You are audible, but sometimes there is like static.
Wait, 1 second. Hello. Is this better?
Yeah.
So he is asking that can you brief about the common techniques for style conditioning or speaker conditioning with respect to speech synthesis?
Okay. So speaker conditioning and style conditioning are usually kind of two separate things, right? So if you have like a data set or you know your speakers well in advance, like it's kind of like if you're only going to use a particular set of speakers, then I would say speaker ID, like conditioning using speaker ID is really useful because it works really well because you have seen all the speakers and you can condition on exactly which speaker you want the synthesized speech to sound like. But if you want the condition where you don't know in advance like what speaker will be coming in and using your method, so then you need to use like an encoder which encodes a reference utterance, right? So you take a sample of the target speaker speech and then you kind of train, like you kind of, there are methods like for example, this speaker verification TTS, right? So what they do is they train the speaker encoder on a speaker verification task. So they input multiple speech segments and then try to verify which segments belong to the same speaker and which segments belong to different speakers. So in that way, they train the speaker encoder for a speaker verification task, and then they use the encoder or the model which was trained as like an encoder, and they to kind of give you some kind of embeddings which can distinguish between different speakers. So they given a target speaker's reference utterance, it goes through the speaker encoder which was trained on verification. So it gives embeddings which are discriminative in terms of speaker, and those embeddings are used for speaker conditioning. So this is the speaker conditioning part. Now the style conditioning part comes in where it's slightly different because in the speaker encoder, when you train for speaker verification, you train the model in such a way that it does not matter how the speaker is speaking, it should align itself with the same speaker, right? So even if the speaker is speaking in a happy tone or a sad tone, both of them should map to the same speaker embedding. But in style conditioning, the idea is to have like variation within the same speaker's utterances, right? So style conditioning is usually like done like kind of like as part of the TTS pipeline itself. So they just take like the reference utterance and then use a conditioning module, which is like I think I mentioned in the previous one as well, called global style tokens. So which is like kind of like an attention map based approach. So they kind of take the reference utterance, go through the conditioning module, and then select. And basically, the conditioning module gives you some weights to select or apply to the style token. So there are a set of tokens which are combined like in a weighted sum kind of way. And so the weights are given by the style conditioning layer, which is derived from the utterance or the reference utterance, which is then used by the synthesizer. So what this allows us to do is, in case you don't have any reference utterance, you can actually manually tune the weights of the different style tokens to kind of produce speech which is varying to different degrees, like pitch wise or speaking rate wise, etc., etc. And finally, the mellotron method. So mellotron method, it kind of combines all of these into one method. So where they use the speaker ID to do speaker conditioning, they use GST, the global style tokens, and they also use like explicit pitch contours. So what this allows them to do is, it kind of, given, let's say, a music track, based on the pitch contour of the music track, they can synthesize like a singing voice, where the voice also kind of rises and falls based on the pitch contours in the music. So this is a very interesting work that was published in 2019. Yeah, so I hope I have answered the question.
Yes, and Azhar sir is also asking that in case of tonal languages, what is the approach to tackle same text, different meaning in text-based NLP?
Okay. So I mentioned it here. So usually in text-based NLP, these are the two things which are used. So one is the text itself. So you put some special pitch action marks, or use some kind of like in the phoneme dictionaries, you use some kind of special phonemes to emphasize certain like tones or some things like that, or you use grammatical marks, right? So it might be really like I mean, not very intuitive, because in English grammatical marks are like very common, right? Like grammatical marks are regularly used to define the meaning of sentences or words. But in a language like Japanese, there virtually is no grammatical marks except the period. So, and also, as you can see, there are no spaces in between the words as well. So in languages such as these, so it's inferred from the context, right? Where instead of looking at this sentence as like in isolation, you look at it in as part of a larger text, like a paragraph or something like that. So, or you take a look at this this character, and then you see how it interacts with the nearby characters or nearby words, and so on and so forth. So in the current like NLP systems, so they use like these kind of the text itself to specify like particular accent marks and or some kind of some special tokens, or from the context, that is the word in sentence or sentence in paragraph. Yeah.
So next we have a question from Sisir sir. He says, for multi-speaker TTS, which model do you suggest? So first, is it less response time, or the one with less model size? Third, which framework to build?
Can you
Yeah.
repeat, because your voice kind of broke in between.
Okay, I'm sorry. I'll just repeat. So sir is asking that for multi-speaker TTS, text-to-speech, with speaker encoder, which model will you suggest? So first, is it the one with less response time, or one with less model size, or with which framework to build?
Okay. So so if you want to like train it from scratch, then I would pay more attention to the task, like whether you are training it for speaker verification or something like that. But if you are looking for a pre-trained model, like you want to use a pre-trained model which somebody else has already prepared, then it also depends on like your application, right? So if you want real-time performance in your application, you would have to go for the one which has the lowest latency. So basically, in that case, you cannot have models which use LSTMs, for example, because those are autoregressive, and you cannot, like, you have to wait for the entire sequence to be processed and only then get the outputs. So it depends on your application, but task-wise, I think the speaker verification TTS is quite good, and because it is highly discriminative in terms of the embeddings being like separated in the kind of the latent space based on speakers. So the speaker verification TTS I would recommend, and I think there are quite a few publicly available implementations as well as pre-trained models, I think, as part of the ESP.NET package as well as Mozilla's TTS library. So you can maybe use that directly in your work as well.
Okay, thank you, sir. I think we don't have any more questions on YouTube. I'd like to ask one question, sir, from my side. A lot of people go for like directly to masters and PhD, and some work have some work experience and then they shift. So, what was your motivation, sir, like behind going back to academia?
Okay, I think that's a very good question. So when you complete your bachelor's, especially in India, BTech, when you do it, so you are you have two options, right? You study for GATE and then apply for GATE and go into MTech or something, or you take up a job. The job side is kind of very lucrative, so that's how I got into the job. But then when I started working, so initially I was like kind of doing the engineering stuff, but then I kind of got tired of doing that kind of thing, and then I wanted to know more about how things work rather than just building things. So within my company itself, I tried to move into a research kind of a position. So as I did my research in Sony, so I kind of got this appreciation, or like I really enjoyed doing research, and so I wanted to learn more in a free environment, right? So it was quite free in my company as well, but then you still had to be confined to the source separation domain. Like you can do all your research you want, but you have to be confined to that domain, to the team that you are a part of. But I wanted to learn more about other things as well. Like I wanted to learn more about NLP, I wanted to learn more about speech and etc. So then I thought like maybe it's a good idea to go move into the academic side of it and see how that works out. And while doing that, why not get a degree? So yeah, that's how I ended up coming back to academia. But now when I'm here, I kind of like, as I said previously as well, I think I see the pros and cons of both. And if you saw my the introduction slides, I'm also working as a junior research engineer in a startup here along with my PhD. So I'm kind of trying to enjoy both sides of the coin. Yeah.
I see. Thank you so much, sir. I think we don't have any more questions on YouTube or in the chat here. So I think with that, I'll again like to thank you, sir, for this talk, as you gave a very good overview, and also you went in depth to the topics in how you had those patents at Sony, then audio source separation, and also you gave us a bit of your journey of how you got into the university. So I think that will also help a lot of people. And then finally your current research in speech synthesis. So as we have members from both from the undergraduate level to a lot of experienced people, I'm sure it was equally enjoyable for all of them. So with that, I'll again like to thank you, sir, and we hope to see you again at some IE event in the future as well.
Sure. And thank you for having me and giving me this opportunity. Yeah, thank you so much.
Thank you, sir.